Good morning. This is E637, and I'm Charles Bouman. We had a little snafu with the last lecture that something happened. The bits were lost in space, and it didn't get captured. So instead, I posted, or I think the EPE people posted a lecture from 2 years ago that covered substantially the same material. But at some point, I'll try to redo that lecture. And repost it, but at least there's something there for you to take a look at. One announcement I have to make, which unfortunately is very important. It's stupid, okay? What can I tell you? But we have to do it. Courtesy of the federal government in the United States of America, we're required to provide some kind of crazy information for them about like something or other. So everybody in the class has got to make sure they email the TA before the end of the week that they're alive, okay? So that email can either be that you sending in the homework, or saying that the homework's not done yet, or just saying, hello, how are you? I'm taking the course, okay? But you've got to register. Basically, you got to kind of. So you would say, well, I've registered already, okay? But the federal government felt that was too productive, and that we needed to register again. So you have to basically send an email to the TA saying, I'm here, hello, okay? So that I can check a little box on a website. Okay, so please do that so that I can check everybody's box. Okay, and if you know anybody who else, let them know that too. Okay, all right, good. So, and I think, do we have any questions? Okay, so yeah. So today we're gonna. So last time we spoke about cameras, and we've of course talked about the continuous and time and space Fourier transform. So one very, two very beautiful applications of that are digital imaging in the sense of photography, which we've sort of talked about in the last lecture. I think we kind of covered that at a high level. And two other very beautiful applications of that are computed tomography and MRI imaging, or magnetic resonance imaging. So we can sort of study both of these applications using the Fourier transform, and without getting into sampling and discrete time systems. Of course, in real systems, these things are all done on computers, so they have to be done in discrete time and space. But at least at this point, we can use the continuous time and space Fourier transform as a theoretical basis for analyzing these systems and having a basic understanding of them. So we'll cover that now, so that you can see an application before we go on to the discrete systems. In the class, I try to intersperse the theory with the applications, so you kind of see how the things get used. So
I think there's microphones on.
Is this microphone working right here? It's supposed to be. Hello?
It's working.
Oh, it's working. Okay, good.
But we still have ours on. Do you want these on?
Oh, no, you turn those off unless you... I think the way that those work... Oh, I think they're supposed to be on all... I think they're for you to play bongo drums. Okay, but I think they're supposed to be on all the time.
They're live all the time. However, if you beat on the desk, you'll be able to hear beating on the desk.
Okay, so avoid beating on the desk. Okay, and then that way, if you have any question, the people in TV land can hear your question as well as my answer. Okay? Good. So you can all be movie stars. Okay, so we're on to any questions then? Okay, so let's go on to tomography. Let's see. So we can... Actually, I'm going to change the order in which I go through the slides a little bit. Can we flip over to the slide? To the paper? Oh, there we go. So that's a CT scanner. They used to be called, and in fact, a lot of physicians still call them CAT scanners. So I think CT stands for computed tomography, and CAT, I think, was, I guess, sometimes the acronyms is a little uncertain what they stand for, but I think it's computer assisted or tomography. So they took the A out, and now they usually refer to it just as CT. That's the more sophisticated term, really, CT. So CT scanners look like this, and it's an example of a 3D imaging modality. Another 3D imaging modality is MRI that we'll also talk about. People often confuse MRI and CT because, from the point of view of the patient, it's just another big white tube that you get into, and it makes a picture of you. Okay, but they're completely different. Okay, I mean, superficially they seem the same, but once you get into the issues of what they're really doing, they're totally different. Okay, not only is the physics of what's going on very different, but the mathematics of what's going on is very different. Okay, and we'll see that. As a matter of fact, they represent two very distinct different techniques. There are many modalities that use tomography to reconstruct images, not just CT. CT is a specific one. I think I'll mention in here, I don't know if I will, okay, but there's another thing called PET, or positron emission tomography. And PET uses also tomographic reconstruction as well as CT, but the imaging modality is quite different because the physics behind it is very different. And there's all kinds of applications in which people do tomographic reconstruction. And more generally, we'll see that tomographic reconstruction is really an example of an inversion process where you basically have a linear transform and you're trying to invert the linear transform. Okay, so tomography CT is a special case of a broad and class of methodologies that have application in medical imaging, also non-destructive testing or sensing. As I know that we have people in the audience here in the class who are interested in applications like radar, SAR. It can also be viewed as a problem in tomography sometimes. So it's sort of a special case of our broad class of problems of what I would say would be growing importance. So and then MR is not a form of tomography. Magnetic resonance imaging, MRI or MR, is not the same. It's distinctly different, has a different kind of set of equations, and we'll talk about that. So we'll learn about the two, sort of canonical examples, you might say. Okay, now in CT, like I said, it's kind of a white donut. The patient lies down on the bed, and the bed, you hear a whirring noise, and then the bed translates through here, and then the technician calls on a little phone, and they go, Mr. Bouman, you can get off now. Okay, and then you get off, you go home, and then they call you up later, and the radiologist is a physician, so they're an MD, medical doctor, or they're licensed to practice medicine, and they actually read the scan. Usually the radiologist doesn't actually physically take the scan, but they read the scan, they look at it, and they make a diagnosis from it. So, and the scan is a three-dimensional object. So the difference between CT and MR and older imaging modalities like X-ray, the classical planar X-ray, is that this is three-dimensional. And see, it's three-dimensional, and classical X-ray imaging is two-dimensional. Okay, so that's hugely different. You might say, well, this is a 3D image. This is a 2D image, but this is a 2D slice of a 3D reconstruction. You have voxels in 3 dimensions. In planar X-ray, you just you put you have the person lying down on a bed, and then you have an X-ray source, and you have film underneath there, and you have the superposition of everything. So when you look at the image, you see backbone superimposed over heart, superimposed over liver. Okay, so because of that, it's much more difficult to make a diagnosis from what sometimes they call this as a chest X-ray. It's a planar X-ray. Okay, and when you have a source of light, of X-rays, and you have, in the old days, of course, you had photographic film. Now you may have a digital focal plane array, basically, that can capture digitally and measure the number of X-ray photons, and you form a 2D image by the and if you basically you take the log of this thing, and they usually reverse it so that the points with very few photon counts are displayed as white, okay, and the parts with very little a lot of photons counts are displayed as black, okay. So that way, soft tissue looks dark, and bones look light. Okay, that would be a classic X-ray that you'd be used to seeing. You could display it any way you want, but that's the way people are used to looking at it, and that's the way radiologists are used to looking at it. Okay, but this is 2D. Okay, this is 3D. Okay, so how does that work? How do you form a 3D image of a person without actually slicing them up? Okay, which most people will object to. So how do you do that? Okay, so well, that's where the magic of tomography comes into play. So in tomography, what happens is that, this is kind of a strange-looking person, but imagine that this is what a person looks like, okay? So they're like this. And here the person is uniform density, but it could be that they don't have uniform density. It could be like that's their backbone, okay? And what will happen is that the idea is that in tomography, tomo means slice. So this is Greek, I think, for slice. So in tomography, what you're trying to do is take slices through something and use that to reconstruct what the thing looks like, okay? So here, in the planar X-ray, at every point, you try to measure the line integral of the density through the material. Now, what's density? What's line? What does this mean? I'm going to be more specific in a moment, but I'm giving you the general idea. So if you get the projection through the object at each point, so at every angle, theta, you get the 1D image of projections. Mm-hmm. And then if you have that at every angle, then you can reconstruct the image. So it's as if, like, if I'm in a room. Okay, could we come on to show me personally? Like, take the camera onto my, yeah, right there. So if I'm looking at something and I have an object here, okay? So, and I'm looking at something with the object, and I can't see around it because the object blocks my view, okay? So if I tilt my head, I look at different angles, I can see what's behind the object, right? So that's the intuition behind tomography, that by looking at different angles, you can get different views, and you can try to find a consistent interpretation of all the views. If you only have a single view, there's information you've lost. But if you have lots of different views, you can put them all together to have a single 3D interpretation of what's going on. It seems like a massively complicated problem, and it's not obvious how to go about doing it, and that's where the mathematics is going to come into play. So let's go back to the slide. Okay, so here, so we're going to have this projection, but we're not going to just have this projection at one angle. We're going to have it at all angles, okay, and then we're going to have to reassemble it. So how do we reassemble it? Well, there's going to be a thing called, so by the way, f of xy, that's the thing we want to reassemble. F of xy is a function of x and y, okay? And then the projection of that is going to be p sub theta of r. So P is a projection at a particular angle theta. We're going to get a function of r. So we're going to the actual tomographic instrument makes measurements of P of theta r from f of xy, and then the question is, so this is the physical world. This is our CT scanner, and then from this we want to go back and get that. So this has to be mathematics. Okay, so in this direction is the CT scanner. This is the scan. And this is the math reconstruction. So this is computed. Okay, and this is called inversion because the physical system measures something, and then from those measurements you want to invert that to get back into the original quantity. Okay, so how are we going to do about doing that? Well, there's a beautiful theorem called the Fourier-Slice theorem that tells us how to go about doing it. Now, the Fourier-Slice theorem is like the atomic sledgehammer of CT, okay? But it doesn't exactly tell you, it gives you the beautiful theory to solve your problem, but it doesn't really quite go about telling you how to actually get the problem solved, okay? It doesn't exactly tell you what you should do on the computer. And there's lots of ways about using this theory to get the answer, but a lot of them are not very practical. So the practical way of actually getting the reconstruction is called convolution back projection. Well, there's actually lots of ways you can do it, but the conventional, most widely used method is called convolution back projection or filtered back projection. And that's actually the technique that we're going to use to actually do the reconstruction. Okay, so now, so I think I talked about this. Anatomical imaging modalities, chest x-ray, I talked about that. Computed tomography, I've talked about that. And magnetic resonance imaging, I've talked about that. We're going to talk about it in a lot more detail later, okay? Now, these are all anatomical imaging mechanisms because they actually show you what the human physical form looks like. I mean, they show you the physical location and position and shape of your bones and the soft tissue and so forth. But they don't necessarily tell you what that tissue is doing, okay? What's very interesting is what's called now functional imaging modalities. Functional imaging modalities take this a step further, and they actually look at what is going on biologically in the tissues that are being imaged. So SPECT is an example of a functional imaging modality. PET, which is also an fMRI, functional MRI. In addition, I mean, CT can do some functional imaging when you use contrast agents, but it's not its primary strength as a modality. It's not what people normally think of it as. Yeah.
So would an example of this be when you see in like hospital shows and you see like the brain lighting up different colors? Is that the kind of thing?
Yeah, that's functional.
Okay.
Right, absolutely. That's functional imaging. So an example of that in MRIs, you can actually do studies of what people are thinking. You can study how their motor cortex or higher level cognitive functions are behaving. Right, that's functional imaging. And then there's kind of the next thing that goes beyond that, and these are kind of fuzzy boundaries, honestly. Which is called molecular imaging. And molecular imaging, you're actually looking at the biological processes in cells, like gene expression and things like that. It's sort of a step beyond functional imaging. So now in CT, the way it works is you have an X-ray source, and then the X-ray photons come from the source, and they, we'll talk about this in a minute, but basically the assumption is that the X-rays travel along a straight line, and as they're traveling, with each increment of distance, there's a certain probability that they're either absorbed, whatever that means, or that they continue on. So you can't create photons. They're only created through the light source, so as it's passing through the tissue, they can only be absorbed. And when they're either absorbed or they continue on, is the assumption. So they travel in a straight line or they stop. Okay, so it's like it's as if you were like you were shooting BBs out of a BB gun, and the BBs were going through some kind of material, and there would have some probability of stopping it at any position. Some of them got further than others. Like that, right? But you can't suddenly create a BB, okay? Now, what ends up happening, though, is this approximation is not exact, because in fact, the way a photon is absorbed is it's actually scattered. And when it's scattered, its energy shifts. Okay? But when a scatter event occurs, what really happens is the photon goes in a different direction. But usually, the hope is that when that scatter event occurs, the energy shift of the photon is large enough that the detector is no longer sensitive to it. So basically, you just don't detect the scattered photons. But the scattered photons could turn into light, visible light, because the energy could be reduced that much. Or eventually, they turn into heat absorbed in the material. But the way we think about it is that this doesn't really happen. There's no scatter. Okay, it just goes through a straight line and either stops or goes. Okay. Now, that brings to what's called, I forget the name of this. This is kind of the law. This is a name, and I'm forgetting what, Beer's Law? I guess it's called Beer's Law. So, so what happens is that this shows the attenuation of a photon. So what we need to do is mathematically, we need these projections. And I haven't told you how we're going to get them yet. We need to measure them with a physical instrument, okay? So how we're going to do that? Well, what you can think of this is that you have an X-ray source coming through, and you have a pinhole collimator. A collimator is something which basically you might think of it as sort of focusing the beam of X-rays, but with a pinhole rather than a lens, okay? You can do that reasonably effectively with X-rays because the wavelength is so short that you can get pretty high. If you tried to use a pinhole camera for optical wavelengths, it would be not very effective because you get so many diffraction effects. But the wavelength of X-rays is so short that you can use a pinhole to focus them reasonably accurately in terms of physical distances, okay? So with a pinhole here, the X-ray sources can be thought of as traveling along a line. And then the question is, well, what's the number of photons per unit time, or the number of photons as a function of position along the line? The material, and we assume that the material has some density mu of x. So you can basically write a differential equation down, okay? Okay, so first of all, the distribution, the probability distribution of the photons is Poisson. So if you count photons over a fixed period of time, the probability density, the probability mass function for that number of photons is Poisson. Okay, and this is the Poisson distribution, and the mean of the Poisson distribution is lambda sub x. Okay, or lambda is the mean at position x. So y is the number of photons at depth x. So the expected value of y is lambda. Okay, x is the distance. So you can write a differential equation down. So basically what you do is you say this. Okay, if you look at an increment, so you have these photons and they're traveling through here, and you look at an increment of distance. So this increment of distance is dx. Okay, so the and the photons the average number of photons entering into here is lambda x, okay? So what's the average number of photons that come out? So, well, how many are absorbed? So if you take lambda x, that's the expected number of photons that go in, right? You multiply it by mu at the position x, which is the absorption, and you multiply that by the distance dx, okay? That should be equal to minus delta lambda, because, okay, lambda is a positive quantity, mu is a positive quantity, delta x is a positive quantity, but the number of photons it's a change in the number of photons is negative, right? Some of them go away; they're absorbed. So this will become delta lambda, right? So basically, you can write a differential equation. You get that d lambda x dx is equal to minus lambda x mu of x. Okay? So you can integrate that differential equation. And the integral of that differential equation, you can solve it, is lambda of x is equal to lambda of 0 times e to the minus the integral from 0 to x of mu of t dt. So now, if I take this, so how did I know this is true? Well, I knew it because, I've been teaching the course for a long time, right? Okay, so, but given that I just knew it, okay, how do I check that it's correct? I can differentiate this, plug it into that differential equation, and it solves it. Now, we know, if you've taken a course on differential equations, the solution to a differential equation like this must be unique, okay, given a boundary condition. And the boundary condition here is this. Lambda of 0 is lambda 0. So this is the unique solution to that differential equation given this boundary condition. So what does this equation look like? What is it telling you? It's saying that the lambda that comes out is the lambda that goes in times e to the minus this. So this is the attenuation factor, okay? And it's the absorption of the material, the density of the material is always positive. So this integral is always positive. So you're always going to make the number of photons that come out smaller than the number that go in. Okay, so what I can do now is just go a little further with this. I can say, oh, well, I get that if I can lambda of x over lambda of 0, so the ratio of the number of photons out to the number of photons in, right, is equal to e to the minus the integral of 0 to x of mu of t dt, right? Mm-hmm. And if I take the log of that, well, I get that the log of lambda of x over lambda 0, if I get the negative of the log, okay, is equal to the integral from 0 to x of mu of t dt. By the way, what's t? Well, t is nothing. It's just a dummy variable. I can pick any letter I want here. I could make this any letter, right? And my personal favorite letter to put in there, actually, whenever I put letters in, if some of you may know this, I have a personal favorite letter that I always put in for any letter that can be anything at all. And it's usually the happy face letter, okay? But you may have another choice, okay? You can. I've also experimented with using small homes, okay? Okay? Or, whatever. You could have a little dinosaur. Go to town, enjoy yourself. Put anything you want in there because it doesn't matter. That variable can be anything, right? It doesn't matter, okay? It has no physical meaning in this problem. It's just the integrand, okay? Okay. So, anyway, this thing here, this is the log, this log ratio. Now, the lambda x out is always going to be smaller than lambda 0 because you only absorb photons. So when I take the log, it's negative. So when I take the negative, that's going to make a positive. So this will be a positive quantity, right? And this integral, so this positive quantity here is going to be that integral there. So this is what we needed because this is the measurement. This is measured. You measure that, and this over here is what we need to know. That's the line integral we needed to know, okay? So we could do the tomographic reconstruction. Because remember, we needed the line integrals. Let me just get the picture. There's the line integrals. We needed these line integrals through here. So that's what we're going to do. So the physical system, let's just kind of review what this is going to look like. So the physical system is going to be this. We're going to have a source of X-rays. X-rays will go over here, okay? And then here we have a detector, okay? So the detector will count the number of X-rays. Okay, so this will be lambda, 1, okay? And we'll have an object here, okay? And now what you really do is you do what's called an air calibration. In other words, you remove the object and you measure the lambda with no object in there, and you get lambda 0. So that's the calibration, right? And whenever you have a physical system making a measurement, you always have to calibrate it. So if you have a camera, you have to take a picture with the lens cap on. That's your dark current, right? Here, in this case, for a CT system, you take everything out of the CT system, you make a measurement with nothing in there. That's air, okay? So this is the lambda you get when there's nothing in the system. And then what you do is you make the measurement lambda when there's something in the system. They do this in the morning before you get there. So in the morning when the technician arrives to work, the first thing they do is they calibrate the system in the morning before they start up, if they're doing the right thing. Okay. Then what they do is they take the log of lambda 0 over lambda 1. This is a positive number, right? And the log, okay, so that's going to be positive. And that's your projection. Okay? Everybody clear on that? So, that's the physical measurement that you make. Now, once you have the physical measurements, now we still have the problem that we have to actually invert it, okay? Let me just take a slight detour here at this point and point out that there are other ways you could have made that. So this gives you, this is how you calculate, this is the line integral. Integral. You need the line integral. There are other ways, other physical systems for measuring that line integral. Yeah? But I left the minus sign off. Right. So you can do it either way. So you can take the log of lambda 1 over lambda 0, and you can put the minus sign there. Right. Either way. But this is how you measure the line integral. There are other ways you can measure the line integral. There's a thing called a PET scanner. So, PET scanner, CT scanner, hey, they're all the same, right? There's really no difference. Look. There's nothing else to cover, right? They must be the same. No, they're not the same. Sure, I mean, the plastic cover looks the same, but once you take that off, everything's completely different, okay? It kind of reminds me of the old Monty Python line where they said, it's not just the words you use, it's the order you put them in, too. Okay? So, these are PET scanners. These are CT scanners. PET scanners are... if you have to go to get a CT scan, well, you know, it's probably not a very good thing. I mean, you probably broke your bone or something bad happened. You fell, you know, something. Or it wasn't your best day of the week, okay? But don't go to get a PET scan because then you're probably pretty ill, okay? These are mostly used for oncology applications. But the good thing is that PET scanners are extremely valuable because once you get a PET scan, the oncologist can actually do something to help you. So it's a very good thing, okay? But still, I prefer not to know that you'd had to go. Okay, anyway, so the PET scanner is here. And actually, the one reason these guys look the same is that almost every PET scanner that's sold today contains a CT scanner. They just kind of throw it in for free. So they took the PET scanner, and this PET scanner is pretty expensive to start off with. CT scanners are like inkjet printers for medical 3D imaging. They're like the sort of they're the go-to guys for medical imaging because they're relatively inexpensive. Okay. Okay, I'm not an expert on this, so any number I say is probably wrong, which is why I'll say it. But I think the reimbursable rate for a CT scan, when all said and done, costs about maybe $300. Okay, on the order of that, you know. If you look at your bill, it might be for $10,000, but then Medicare negotiates, and they negotiate down to $300 or something like that. Okay, so these are like $300. A PET scan is much more expensive. Because it's a more complex technology. Or it's not so much that it's a more complex technology, it's just a more expensive technology to fabricate. So they actually attach a CT scanner to it. That's one reason they look the same. And and the physicians, radiologists like that because what they do is, see, this looks like a CT scan, and they superimpose the PET on top of it so that PET will just be like, you'll see, first of all, the spatial resolution of PET is low. So you'll just see a blob, and it doesn't have a lot of spatial definition. And the blob, I have to back up slightly. In PET, what they do is they inject a radiotracer. So what happens is that they inject you with a radioactive tracer. So a typical tracer would be like FDG. FDG, which is fluorine deoxyglucose. It's basically sugar with a fluorine molecule attached, but it's not a normal fluorine molecule, it's F18. So F18 is an isotope of fluorine. It's got a half-life on the order of something like half an hour, 20 minutes or something. So if you recall it's got to be longer than that. Anyway, it's long. Okay, so you want a half-life that's long enough that you can use it, because the problem is that you either need to have cyclotron on premises so you can make the F-18. So in other words, you actually have to have like a nuclear physics experiment on premises, okay? Or you have to have somebody locally, like say within 50 miles or something, who can produce the F-18 in high concentration and then transport it to your location with a courier. Okay, so the F-18 injection might cost something like, I'm making these numbers up, but they're probably not too far off, maybe $200 to get, because somebody has to actually deliver a dose of F-18 that's already had radiochemistry applied to it, so it's attached to the FDG. So you have to make a distinction. This is a nuclear issue, right? F-18 is a nuclear isotope. This is a chemical issue. Once they have the nuclear isotope of F-18, they combine it chemically to make FDG, which is basically similar to glucose. So your body, now, it turns out, like, for instance, this is very interesting. I don't know if everybody's ever heard of heavy water, right? There's isotopes of hydrogen. So an isotope of hydrogen has 2 protons, okay? So you can make water out, I think... okay, hold on. 2 protons is deuterium, and 3 is tritium, or something like that. Do I have it right? Okay. So you can make heavy water. You can use the isotope of hydrogen, attach it to oxygen, and make water. Okay, but chemically, that water is different than regular water. If you drink it, it's not too good for you. Okay, don't go about drinking heavy water. Okay, and it is heavier, right? Because you've got 2 protons. So you have H2O, right? So there are 2 protons here, 2. Basically, electrons don't weigh anything, right? So, well, they do, but not much, okay? So this is 16, so that's 18, right? So if you have heavy water, it would be 4 plus 16, so that would be 20. So it weighs more, okay? It has higher density. You don't want to drink this stuff. It wouldn't be good for you, okay? So the F-18 isn't exactly the same chemically as fluorine, but it's close. Your body basically metabolizes this as if it's sugar. And what happens is, it turns out that most cancers tend to, fundamentally, one of the things that causes cancer to be bad is that it grows uncontrollably. So when it grows uncontrollably, it also metabolizes a lot of sugar rapidly. Mm-hmm. So what will happen is that the tumor will basically have a much higher uptake of glucose than the other surrounding tissue, and it will light up. But it's a relatively blurry image. What will also light up are things like, you see the kidneys light up because you're basically metabolizing the FDG and excreting it, right? So that's a pretty typical thing. The bladder and the kidney will light up. So what happens here? Okay, so they superimpose this, and the physician can see where the tumor is located. So this is very powerful technology, because now what they can do is go in there. If they're doing surgery, they can design the surgery to try to take out that tumor if it's hopefully localized and not metastasized, okay? Or they can also design oncology drugs that are, they can do a biopsy so they can get molecular information on that so that they know precisely which cancer it is. For instance, with ovarian cancer, there's many, many, many different types of ovarian cancer. So if you know exactly what kind of ovarian cancer you have, that's much more treatable. Okay, so it's very interesting. It sort of shows the interplay between biology and medicine and physics and mathematics. But in any case, so when the patient is injected with FDG, the FDG floats around. It's metabolized. When it's metabolized, what happens is that the FDG may break down. So, but the F-18 doesn't change, right? Chemical changes do not change the atomic structure of the molecules. So the isotope of fluorine, whether it gets metabolized or not, still remains. And it's radioactive, so it's unstable. The nucleus is unstable. And when it breaks down, it releases 2 gamma rays. Oh, no, I'm sorry. When it breaks down, well, there's various things that happen. Okay, so I'm going to oversimplify this. But when it breaks down, it releases so this is the F-18 here. When it breaks down, it releases a positron, okay? The positron annihilates with a nearby electron. So when the F-18 decays when you have nuclear decay of the F-18, it releases a positron. The positron floats around and very rapidly finds an electron. The electron and positron are antiparticles, so they annihilate. And when they annihilate, I'm not drawing this exactly right, okay? Let me redraw this because the physics of that was wrong, okay? So this is F-18. The F-18 produces a positron. The positron annihilates with an electron, okay? And when the I'm exaggerating this. When the electron and the positron annihilate, the only thing that's left is energy. So you have to have two photons. And the photons you get are two gamma particles. So this is gamma and gamma, okay? But the momentum of the gamma particles is not exactly zero because the positron had some momentum when it annihilated with the electron. So this angle here is approximately 179 degrees, okay? But it's pretty close to 180 degrees. So so what ends up happening is this. When it annihilates, you get two particles that travel in opposite directions, and then you have a ring of detectors, okay? So you have a ring of detectors like this. And it's really an amazing piece of electronics when they build these things. So each of the detectors has a system that counts photons. When it sees a photon, it registers the photon, and it registers the time of the photon. Now, if two detectors, you know that if there's an annihilation occurs here, how far does a photon travel in free space in 1 nanosecond? Well, we covered this in the last lecture. So it's in free space, how far does light travel in 1 nanosecond? Remember? Remember it's the person who was, what's her name? The person who wrote the first compiler. I forget her name.
Hopper?
Yeah, Grace Hopper used to talk about this. How far does light travel in 1 nanosecond in free space?
Oh, you said it was like a foot or something.
It's about a foot, okay? It's actually about 30 centimeters. So it travels about 1 foot, 12 inches, okay? So the ring here might be like, I don't know, a couple feet in diameter. There it is, right? You have to get inside of it. So it's a couple feet. So the difference in time when these two things arrive is on the order of like a couple seconds. A couple nanoseconds, not a couple seconds, okay? So basically, if you have two events that occur, so if Ti and minus Tj is less than, say, I don't know, let's make up a number, 10 nanoseconds. I think that's a pretty typical number that they use. Then you declare it that those must have been a coincident event that occurred from the same underlying decay of an F-18 isotope. So you can count coincident events. So every time you have, so you count all these coincident. So if you have 512 detectors, you have 512, roughly 512 squared. Well, you actually have 512 times 511 divided by 2 virtual detectors, okay? Because that's all the unique pairs you have of detectors. So for every unique pair of detectors, you have a virtual detector. You count how many annihilations occurred along that detector, and you get a line integral. So you get a line integral. So the point is, this is another technology where you can get a line integral. Once you have a line integral, mathematically, it all boils down to the same inversion process. Okay, but the underlying physics of the acquisition are quite different. Are there any questions about that? Yeah.
Presentation, how long does it take?
That's an interesting question. Well, it's interesting. So the first thing they do is, maybe you can take the camera on me. So yeah, we don't look at the paper. The first thing they do is they inject the FDG, and there are other tracers that are used too. And then usually what happens is they have the person, wait maybe about an hour, and that gives time for the FDG to be metabolized by the tumor, okay? And guess what? During that period of time, they have them sit in a room by themselves. You know why? Because they're radioactive, okay? Okay? As a matter of fact, I don't know what they do about bathroom facilities either, but that's another matter. Okay. But the nice thing is the F-18 doesn't have, if F-18 had like a 200-year life, half-life, then that would be a problem, okay? Because then it would take a long time to dissipate. Since the half-life is relatively short, I think it's on like an order of maybe I'm wrong, but I think it's on the order of something like an hour or half an hour. I think it's like about a half an hour. Then after about a day, it's mostly all gone, okay? And then they image them, and the PET scan is pretty slow, so it can take like easily, it could be like maybe 5-10 minutes, okay? And the image tends to be a little blurry because the patient can only sit so still. And you can do dynamic PET, where you actually measure the response as a function of time. And there is additional information that would come from dynamic PET. But the problem is it's much more costly because you're tying up the machine for an hour rather than letting them sit in a room by themselves for an hour. And the cost of medical imaging like that really is tightly, the fixed costs the variable costs tend to be small. The fixed costs tend to be high. So it tends to be related to how many people you can put through the scanner per day. The higher throughput means lower cost. So a good question. Any other questions? Okay, I think we're almost out of time, but let's see. So now how are we going to do this tomographic reconstruction thing? I'll just mention a little bit. Okay, so it turns out we're going to talk about the how we're going to do this next time, and the first thing I'm going to do is introduce some transformation coordinates. So theta is this rotation, and basically what's going to happen is I'll just give you the answer since we don't have time to derive it anyway. I'll just tell you the answer, and that way you'll know what the answer is before we do it next time. Let me we have, okay, I have a little more time. Okay, if the answer is going to be this. Hold on, where is it? Fourier slice theorem. Okay, the answer is this, the Fourier slice theorem, that it says that if you take the continuous, see, this is the projection at a particular angle, right? R is the displacement. So let me just put the picture up again of this. So this is the object. At a particular angle, we check the projections, which we can get, and so we get a function as a function of R. So we take this 1D function, and we take the continuous time Fourier transform of this 1D function, okay? So that's this. We take this, we take its continuous time Fourier transform, so the transform variable in frequency is rho. Now you'd say, well, why not use F? Well, because it's going to get too confusing if we use F. So I'm going to use rho. Rho is serving the function of frequency. And then, of course, I can always take the continuous space Fourier transform of the 2D object, right? And that's f of uv. So what's the relationship between this and this? Well, it turns out that p of theta rho is just the continuous space Fourier transform in polar coordinates. So it's a beautiful result, because what it means is this. This is how to visualize it. We'll talk about this next time. That if you took the 2D Fourier transform of the object, then when you take a projection and you take the Fourier transform of the projection, you're basically looking at the 2D Fourier transform along some ray at the associated angle. So if you lay these together at all the different angles, you're getting the 2D Fourier transform of the object in polar coordinates. So all you have to do is take the inverse Fourier transform. You just lay down polar coordinates, take the inverse Fourier transform, you're done, okay? But there's a hitch, okay? By the way, go back and look at the proof of this. But the hitch is this. Standard 2D FFTs are done on rectangular coordinates. So doing a 2D Fourier transform in polar coordinates is tricky. It's computationally very expensive. So you need to you would need to interpolate on a rectangular grid. But interpolation on a rectangular grid is also expensive computationally because it's a non-homogeneous interpolation. So what they really do is a thing called convolution back projection. And convolution back projection is a tricky way to get the answer and to avoid all these issues of Fourier transforms and interpolations. But this is the underlying theoretical concept that allows you to recover the signal from its projections at every angle. It also gives you a lot of insight into what information is lost when you don't get all the angles or when your frequency transform isn't, you don't have enough projections. So I think we're out of time. Thanks a lot. It was fun. I'll see you again next week. Bye.